Hi everyone, my name is Amit Gross and today we're going to talk about what is the amount of data required to teach a machine learning model for accurate results. So as you can see, the data, it really depends. It really depends. It depends on the problem that you're solving and the data that you have. So what can we actually do is we have some thumb rules that we can show you. And there are a lot of questions that you need to ask yourself in order to really assess the amount of data that is needed. So as you can see, this is not super accurate, but it will really help you to ask the right questions and what should we need to do in order to really assess it accurately. So one question that you need to ask is the data is labeled? And if it's labeled, is it labeled accurately? So labeled data will help you to ignore the residual data, ignore the noise of the data. So supervised learning really helps us to put some brains or our world expertise in the model in order to learn better, to learn faster. And usually we need less data if we have a really good labeled data. Another question that you need to ask is the training data distribution is similar to the test or actual data distribution? And distribution of the data of the training and the validation or the testing is really important. Um, Otherwise, you'll have some overfitting. So you need to take the data from a population or distribution that really represent the real world or the problem that you need to solve. And this is really important. So don't reduce the data in order to uh, avoid this problem. What is the kind of problem you are solving? This is also really important. So the complexity of the problem. Is it a linear model that you will be using or some complex model that you will be using? Obviously, linear models need less data, and try to really assess and read the lectures and read literature and do some research before you're getting into the problem so that you'll have some direction of how you want to solve the problem. If you want to solve the problem with the deep learning techniques, so usually, as you can see in this graph, you will be required for more performance, more computation efforts, and usually it requires more data than traditional machine learning when you get some manual feature and domain expertise into the system. So if you don't have domain expertise and you just want to throw data on some model, something like we call it transfer learning, then take into account that you might need more data that usually is needed when you have domain expertise. And the more complex the architecture of the model, usually the more data that you'll need. Another really important question is, can you reduce the problem complexity? So let's say, for example, here in this picture, you can see an eagle. So you want to identify eagles in pictures. But can you reduce the problem? Maybe you just want a specific black eagle. And this is something that helps us to reduce the problem. And then maybe instead of using deep learning or a lot of images of many kind of black eagles, then you can just focus on this particular uh, 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 black eagle when you can see his head. And maybe let's just focus on the head of this eagle because it's really unique. So you can identify the colors of the beak and generate some algorithms in order to identify this specific beak. or its specific shape of the head or the proportion of the head to the body. And then you can generate a proper model when you insert some domain expertise or specific algorithms that you know that is very important to identify. And usually when you do this, you'll need less data. So another thing that you really should be careful, but also ask yourself is, what's more important for me? Is it the false positive or the false negative? Okay, so this is the terms of accuracy and recall, and there are problems. Let's take, for example, medical domain or predictive maintenance, when the false negative is more important than the false positive, meaning that if you let's take COVID, for example. So if you have some false positive and you identify that a person has a COVID, so you will send him to the doctor or for other tests to do, and it shouldn't be a problem. But if you have a false negative in this domain, so it means that you say that everything is okay with the patient, but he actually has the disease. So now what you're causing might be a severe illness or even death. So this is really important to understand in your domain, and you need to define it uh, before you're conducting the research or assessing how much data you need. So defining your goal is really important. It's really connected to the previous slide. It means that I want to really understand what should I solve. And for example, if 80% accuracy of a model is enough for you, meaning that 80% of the data will be identified as good results, with good results, it means that you can use maybe less data than you usually need. Is your data is in good quality? Good quality is a big word, but it means that you have a really good process of, for example, labeling the data. Who labeled the data? Is it a machine or is it a human? When you have more uh, problems of false identification. How did you do the validation of the labeling of the data? There are, for example, machine Turks that you can use a lot of people to send the data to, and then they'll send you back the labeling result that they did, and then you can manipulate the data and do some statistical function in order to decide if this labeling should be 1 or 0. Depends on the amount of people that label the data as 1 or 0. So the better the data quality, the less data you'll need. Can you compromise the recall of the model? Meaning, is it okay if I will identify less objects that I want to identify in the data? And is it okay? Because if it's okay, then maybe accuracy is more important than the recall, and I want to identify less objects, but if I identify an object, I need 90 plus precision or accuracy that I can, that it's really an accurate result. And one of the most important, obviously, that needs much more skills from a data scientist, from your head of research, from your chief scientist, is to monitor the model performance while doing the training, while building the model. And this is actually the most important phase that you will really uh, accurately understand how much data do you really need. But this phase happens when you actually doing the research and not before you're doing the research. So as you can see here, so you can see the accuracy versus the data set size. And usually the more data we have, the more accurate we get. But there is some point that the accuracy is not changing. And we need to decide if this is a stop criteria for us in the training or the learning phase. And if this is enough in terms of accuracy and recall. So obviously you'll use some ROC curves and AUC curves like under the curves areas to understand if the model is good enough, and to compare different models in order to see if they're good or not. Checking the F1 score, etc., etc., etc. And this is, as I said, it really depends on the model that you're using. So sometimes you'll just measure the gap from a linear model. Let's say that you chosen to use some mixed integer problems of models, or sometimes you need to check the Hessian metrics in order to understand if your optimization function that, for example, using some gradient descent, if it's good enough to stop, meaning that if you actually reached some global optimum in your model. Thank you.